To understand the idea of partial pressures, it's important to remember the characteristics of gases. If you put all of those ideas together, you should come to the conclusion that the total pressure in a system is going to be the sum of all of the individual gas pressures in that system. If you have two gases, they don't interact with one another, but they're each exerting pressure on the container walls. And this idea has a couple of immediate applications. The first is that if you know all but one of the pressures, you can simply rearrange the partial pressure expression to solve for the unknown. For example, if you have a mixture of gases where the pressure of gas 1 is 7 atmospheres and the pressure of gas 2 is 12 atmospheres, you can find the total pressure. You can also have a situation, again we'll use an example with two gases, where you have two of the values. You have the pressure of gas 1 and you have the total pressure. And you can rearrange to solve for the pressure of the second gas. In this situation where you have a total pressure and you subtract a known pressure to solve for the unknown pressure is a very common thing to do in a lab setting where you're collecting a gas over water. In these types of experiments, you'll have a sealed container that has a pressure gauge on top of it, and inside that sealed container you'll have a gas-forming reaction happening in aqueous solution. And the total pressure in that system is going to be the pressure of the gas that's formed by the reaction plus whatever the water's vapor pressure is. And you can find the total pressure using the pressure gauge, and you can look up from a table the water vapor pressure at a certain temperature. Another thing you can do is work with the ideal gas law. The total pressure for a gas mixture is going to be the sum of all the individual number of moles of each gas times RT divided by V. And this works because RT and V are constant for each one of the gases in the same container.